Okay, and in chapter 13, the first section is titled "What is the Power of a Point?" This is really getting at what is known as the Powerpoint Theorem. So this video will talk about more of the theory and go through the proofs of this information, and then the next video will actually work through some more problems, and as well as the video to follow that. So the PowerPoint theorem says, suppose that a line through point P intersects a circle in 2 points, U and V. Okay, and then what it says, the conclusion of it, is that the product of the distances from P to U and P to V is constant. Okay, so we do have to separate it into two different cases, though. The first case is when that point is inside the circle and the other one is outside the circle. Okay, so if it's inside, we can actually break it up as the product of the shorter length of the chord and the with the length of the longer portion of that same chord, and that should be equal to, for a different chord, the length of the shorter piece times the length of the longer piece. So that product will always remain constant. Okay, and then similarly, if we are on the exterior of the circle, it changes, but not too much. So we would say that if we have a case where we have tangency, that we would just be able to square the length of the distance from the point to that tangent, to the place where it's tangent, that point of tangency. In the case that it's not, we can take the length of the distance from the point to the first point of intersection with the circle, and then the length from the point to the other point of intersection with the circle. Okay, both cases. So PB times PC, that would be constant, as would the length of PA squared. Okay, now we're actually going to go through and prove this stuff. So in the interior case, what I'm going to do is I'm going to create two line segments. Okay, specifically to make triangles. So I'm going to make a line segment from A to D and from C to B. Or so. Okay, so I think that's off by a little bit, but again, forgive the hand drawings here. So what I'm thinking is, right now these two triangles look similar to me, so I'm going to try and use similarity in my proof. So, well, what do I know first? Well, I know I have vertical angles. Okay, so those are vertical angles, so I'm going to say angle AXD is congruent to angle CXB, as in boy, by vertical angles. Okay, and then what else? Now is kind of where I'm thinking angle-angle similarity, but it could be a little tricky. And what I'm going to note is, look at this arc AC. Well, okay, look at here, ADC, that's an inscribed angle. Do I have another angle? Well, yeah, actually I do. ABC is also inscribed to the same arc. So that means that their angle measures are going to be the same. So angle ADX is congruent to angle, I have to be careful here, CBA, BA by inscribed angles opening to same arc. So then from this I get that triangle XAD is similar to triangle X, and this one, so I said that those two angles were, so it would be XCB by angle-angle similarity. Okay, and then once I have angle-angle similarity, I know that the sides are in proportion. So in other words, AD, or sorry, AX over DX is equal to CX over BX. And from this, I get that AX times BX is equal to CX times DX, which is exactly what the Powerpoint theorem said. So I'm done in this case. Okay, next is the proof of the exterior case. So what I'm going to do is I'm going to try that same idea of drawing line segments. So I'm going to draw a line segment. The proof, you will have to prove it for the other equivalent statements in this case, but if the technique for one of them is the same for all the rest. So I'm going to create a line segment from A to D and from A to E. And so my goal is to show that this smaller triangle and this triangle are similar. And let's try that again. It's actually triangle APD and EAP. Okay, I'm trying to show that those two triangles are congruent. So to do that, I first note that measure of angle AED, this angle here, this is actually going to be equal to, so let's get this down, measure of angle AED. Well, that's an inscribed angle, so that's going to be half of the measure, 1/2 measure of arc AD. Okay, but if I look at this, this is also going to be the measure of angle PAD. This is another angle, so measure of angle PAD. Okay, so I have this relationship, and in both cases, PAE and PAD, those two triangles, angle P is congruent to angle P. So then I get out of this that triangle APPD is similar to triangle EPA by angle-angle similarity. And then again, I'm going to set up that side ratio. So PA over PE is equal to PD over PA. And then from here, this leads to PA squared is equal to PD times PE. Okay, and then again, like I said, you can show the others in a very similar fashion, both by doing angle-angle similarity and then setting up the side ratios. And so that is really the proof of the Powerpoint theorem, and in the next video, like I said, we're going to be doing some examples with this theorem.